Right now, reactive synthesis and syntax-guided synthesis are two main approaches in program synthesis. Both of them are very powerful and have active industry applications. However, up until now, the two of them have been mostly unrelated because they solve different domains of program synthesis problems. And in this talk, I'm going to show you how to make these two different flavors of program synthesis combined and make reactive synthesis and syntax-guided synthesis be friends. So let's first look at each approach. Syntax-guided synthesis is one of the approaches to program synthesis, and it takes in two inputs. The first one is a semantic constraint that defines the expected meaning of a program, and this is usually in the form of input-output examples. The other input is a syntactic constraint, often in the form of context-free grammar that defines the possible forms of a function. Then syntax-guided synthesis, or SyntaxGuided, takes these two inputs and then synthesizes a program that satisfies these two constraints. A popular example where you can see the ideas of SyntaxGuided might be the flash fill feature in Microsoft Excel. And SyntaxGuided is great for these sorts of data transformation problems. Reactive synthesis, on the other hand, is a little bit different from SyntaxGuided because you first have to precisely define the requirements of a system, and this often comes in the form of a temporal logic specification. Then, reactive synthesis takes this input and then synthesizes an output, often in the form of a circuit or an automata. A popular example is the AMBA AHB bus controller protocol, which is an industry standard protocol, and reactive synthesis was able to generate a model for it. And reactive synthesis is great for these sorts of control flow problems where you need to define, okay, something must never be true, something must be high and then low, and reactive synthesis is great for those problems. So we have these two approaches to program synthesis, syntax-guided synthesis, or SyntaxGuided, or reactive synthesis. But there's a small catch. While SyntaxGuided is great for these data transformation problems, it's actually hard to define control flow properties. Something must eventually be true, something must always be true, and so forth. And on the flip side, reactive synthesis has a little bit of trouble defining data transformation properties, saying, okay, we need to concatenate these strings, we need to subtract numbers, we need some set operations, and so forth. And the problem is that even the most trivial programs generally have both data and control. So what does it mean to have both data and control? So let's look at one simple example. Let's look at the Linux completely fair scheduler, which is the default scheduler on the Linux kernel. This tries to run the task always that has run for the least amount of time. And this is in parentheses because time is weighted in the sense that if you have a prioritized task, if you run for 1 microsecond, it could be actually book kept as a quarter of a microsecond. And vice versa, if you have a low priority task, if you run for a microsecond, maybe it'll be book kept as 5 microseconds. And so there's a level of control, element of control, because you need to in-queue and de-queue different tasks while you're scheduling them onto the CPU. But you also need to do some data transformations because you need to calculate how long each process has run. And maybe this is not too unexpected because this is a little bit of a complex code, so you'd expect it to have both data and control. However, even if you vastly simplified this and had a scheduler where you only have 2 tasks, and the only thing you need to guarantee is that the first task needs to run twice, nothing else. This is the only thing you need to do for the scheduler. You would still have data and control because you would have a state, you're either running task 1 or you're running task 2. But you would also have data transformations because you need to count the number of executions. You need to count how many times task 1 has run. When you're running task 1, you need to update, okay, I've incremented the number of task 1s that I've run. But if you're on task 2, you should say, okay, I'm not actually running more task 1s. And we can see that even this very simple scheduler has both data and control. So the natural question, since we're in the synthesis section, is, can we synthesize this? And we do actually have a language to specify this, which is called temporal stream logic modular theories, which gives a natural way to specify both control and data. On the control part, you have temporal operators such as globally, something must always be true. Eventually, something must eventually be true, such as common logical operatives, such as and, if, and only if. And on the data section, you have variables like task time 1, which store how long task 1 has run, as well as functions like equality and addition, or constants like 0 or 2. But the problem is that there's no synthesis procedure for this language. There's no synthesis procedure for TSL modular theories. Reactive or TSL synthesis can actually synthesize the control portion, but it only has uninterpreted functions, which means that it doesn't actually know anything about data transformations. It doesn't know what equality means. It doesn't know what addition means. It doesn't even know what 0 or 2 means. And we could use SyntaxGuided to do the data problems. We could use SyntaxGuided to synthesize the data transformation problems. However, using SyntaxGuided, we can't really generate state machines. So we're at a little bit of a crossroads where we have this great language, we have this very simple specification, but how are we going to synthesize this? And we're at this problem because we have SyntaxGuided and reactive synthesis, but we see that they have their problems. SyntaxGuided doesn't have control flow, and reactive synthesis doesn't have data transformations. But maybe we're focusing too much on their weaknesses, because at the end of the day, they're both great at doing what they can do. So instead of just focusing on using one approach, why don't we try to combine them? Why don't we try to use both of them and make them friends? So, ¿por qué no los dos? So that brings us to the key idea of the talk. We can make reactive synthesis and syntax-guided synthesis be friends. In our approach, we get SyntaxGuided to teach reactive synthesis how to solve data transformation problems. Then reactive synthesis can handle the rest. It can handle the control flow problems. The key idea being, we let each procedure solve the problems that they excel at and then communicate. Using our holistic synthesis procedure, we can synthesize this very simple 2-task scheduler that we just saw, but we can actually also synthesize C code for the Linux completely fair scheduler as well. And so let's look at the general overview of the procedure. When we're synthesizing a temporal stream logic modulo theory specification, we can first break it down into the control flow problem and the data transformation problem that's going to teach the control flow problem again. And all of this is going to result in executable code. In the control flow problem, we're first going to extract the control flow specification as a temporal stream logic specification. In the data transformation problem, we're going to try and find and solve the SyntaxGuided functions, which we then translate back into reactive or TSL assumption. And we combine these to get one single specification that we can feed to reactive synthesis and generate executable code. So in order to walk through this process, I'm going to use the example that we saw earlier, the very simple task, 2-task scheduler that guarantees that the first task must run at least twice. So when we have the original specification and the control flow problem and the data transformation problem, here we're going to go through the first step, which is to remove the function and predicate interpretations to get the temporal stream logic specification. And this is fairly simple because all we're doing is removing the interpretations. So the specification is going to look syntactically equivalent. It's just that when we remove the modulo theories part of temporal stream logic, we remove the interpretations of equality and add to make it a pure control problem. Now, the problem is TSL, or temporal stream logic, doesn't know that 0 plus 1 plus 1 is 2. And this is a key idea that we'll bring back later. By stripping away the interpretations, we need to somehow add it back later. And this is the part we do by SyntaxGuided, solving this problem and then telling how to solve it to reactive synthesis. So now that we've got our TSL specification, let's go to the data transformation problem. First step is to derive and solve SyntaxGuided problems. This is a very high-level overview, but to synthesize SyntaxGuided functions, as we saw earlier, we need 2 inputs, the semantic constraint and the syntactic constraint. And we can do the same from our original specification. We first try to find the data transformation that we're trying to solve, which in this case is going from 0 to 2. We need to make sure that when task 1 has run 0 times, it eventually needs to run at least 2 times. So that's our semantic constraint of the SyntaxGuided problem. And for the syntactic constraint, we try to find all the functions that manipulate task time 1. In this case, it's addition, and we can build a context-free grammar out of this. And using these 2 inputs, we can feed them into SyntaxGuided, and then we can output a very simple function, add 1, and then add 1 again. Because as we know from elementary school, 0 plus 1 plus 1 is 2. Or I hope you know that at least. So now that we have all of this, and we've synthesized our SyntaxGuided function, now our next step is to transform the SyntaxGuided result into a TSL assumption. And the problem here is, how do we communicate the SyntaxGuided result into reactive synthesis? Because we have a temporal logic specification, but on the right, we have just a standard function. And the problem is how we translate this into reactive synthesis. And our solution is to transform each level of the AST into a time step of computation. And what this means is we first generate an abstract syntax tree for the function that we just had, and we think back to the semantic constraint that we originally had in order to generate this SyntaxGuided function. And then we translate this into a template that we have into TSL. And it preserves the meaning of the SyntaxGuided problem that we had, which is the precondition, then we apply the program statement that produces the postcondition. And we can easily fill in the precondition part and the postcondition part. And the challenge will be to take the SyntaxGuided synthesized function and then fit it into the problem statement that we have here. And we do this by walking through the levels of the AST. The first level is quite simple. You're just adding 1 to task time 1. And you can write that down in the syntax and semantics of TSL. What's more interesting is the next level of the AST, where we add 1 again. But we note that here, we started from 0, we've added 1, and on the next step, we're adding 1 again. So we need to somehow capture the depth of the AST that we have there. And we do that by using the temporal operator next, which is signified by that little circle over there, which means something is happening on the next step. And on the same vein, we can see that we've started from 0, we've added 1, on the next step, we've added 1 again, which means that on the next step, we should get 2. And this is capturing our property that 0 plus 1 plus 1 is 2 in temporal logic. And through this step, we're actually able to get a reactive or TSL assumption from our original data transformation problem. And now comes the combination step, making them friends. And we're combining our control specification with the data assumption. And the way we do this is by teaching reactive synthesis that 0 plus 1 plus 1 is 2. And here, we first have our guarantee, or original control flow specification, and we're going to weaken it. By weakening it, we mean that we're going to have our SyntaxGuided result as an assumption, meaning, okay, this guarantee only needs to hold true when we have the assumption, only when we know that 0 plus 1 plus 1 is 2. So when we feed this temporal logic specification to reactive synthesis, it says, okay, whenever I see the problem of going from 0 to 2, I know that I only need to solve it when I know that 0 plus 1 plus 1 is 2. So it can use that information. And this allows us to run reactive synthesis because we started from a TSL empty specification, which we didn't know how to synthesize, but now we have a TSL specification with assumptions, which is actually a problem we know how to synthesize, which we can do by feeding it into reactive synthesis. And we saw earlier that in order to synthesize using reactive synthesis, you have a temporal logic specification, which often results in an automata or a circuit. And we can do the same thing here. We can use reactive synthesis, and this will generate an automata. But one of the powers of temporal stream logic is that you can not only synthesize automata, but also executable code. And we're going to show you a very simple case study here, where we can actually synthesize a music synthesizer. So here, the user key presses, or whatever key presses people use on the keyboard, is going to be the control portion, and the data is actually how the music's generated through digital signal processing. So here, I'm going to have a temporal stream logic module theory specification that synthesizes JavaScript code to apply synth effects on music as I play a song like Autumn Leaves. So as you watch the video, please pay attention to the timbre of the music, which is how the keyboard sounds, as well as LFO and FM frequencies. So the effects were applied automatically through synthesis. And we've ran our evaluation on different benchmarks, such as actual C code for the CPU scheduler that we synthesized for the Linux kernel. In summary, we've combined two separate schools of program synthesis, reactive synthesis and syntax-guided synthesis, which are now best friends. We use them to synthesize programs with both data and control, and we use a procedure to create Linux kernel scheduler code or a music synthesizer. The tool is available online. You can feel free to try it out or come find me after the session. And that's all. Yeah, thank you for your attention. And now I'm happy to take any questions.
Hi, this is a really great talk. I do have a question though. The add function that you used is mutating. but when you showed it as a SyntaxGuided solution, you showed it as a pure solution. How do you bridge this gap? If you can say a few words when you decompose it to communicate it.
That's what we do by breaking it down to the AST. So we look at each mutation on each level, and once we have a pure function, we can change it into different levels of mutations that we do over time. And that's how we break the pure function into a mutation over time.
So one thing that I didn't quite understand, that's assumption that you synthesized in temporal logic, and I thought it was a really clever solution, but is it actually equivalent to the original knowledge about, 1 + 1 is 2? Because your formula, I'm not an expert in the temporal logic, but your formula said if in the next step you add 1, right? But what if you don't add it in the next step, but you add it in like 10 more steps? It will still be 2, right?
So that's one of the limitations of our approach, and that's one of the future works that we're trying to resolve, because right now the functions that we're generating are a little bit limited. So that part would be part of our future work.
Since we have some time, I'll ask a question. Do you see a way of using this as a general technique to combine 2 synthesizers targeting 2 different theories?
So by theories, do you mean first order theories or? Yeah. So right now, I think we're using our approach to synthesize any first order theory at all in the first place. And we've used linear integer arithmetic as our first target, but it could be extended to many different first order theories that we could combine with different synthesis procedures.
My question was a little different. So what about your approach is specific to reactive synthesis and some kind of syntax-guided synthesis? I was wondering if you could use a similar idea to combine syntax-guided synthesis synthesizer 1 with syntax-guided synthesizer 2.
That's a great question. So I think our approach mostly relies on the language temporal stream logic modular theories, which allows data transformations to be embedded into reactive synthesis. So that is not part of our approach, but I think our approach could be extended, generalized to combine 2 different SyntaxGuided theories as well.
Thank you. Any more questions? All right, let's thank Won Hyuk again.